This is the fourth video about equilibrium, the fourth PowerPoint. This one's looking at Bronsted-Lowry theory. Now, Bronsted-Lowry, you usually see it written with a slash through that O. Unfortunately, my IT skills and language skills aren't good enough for me to do that. So, what we're going to be covering is a definition of acids and bases as described by the Bronsted-Lowry theory. We're also going to be looking at what weak and strong acids are, what the differences in them are, and what those terms actually mean, and what weak and strong bases are, the terms and what they mean. We will also be calculating some pHs in this section. It's using a different formula from what you've used so far. Right, we need to know what these definitions are. We need to know that an acid is a substance that's capable of donating a proton, an H positive ion. We need to know that a base is a substance that is capable of accepting a proton, an H positive ion. This is if we're asked to state the Bronsted-Lowry definition for an acid or a base. Under this, we also need to know that every acid has a conjugate base. It loses a proton, so our conjugate base forms when the acid loses a proton, and that every base has a conjugate acid. This occurs because the base will gain a proton. Okay, so conjugate base goes with acid, conjugate acid goes with base. Similarly to when we were looking at reduction and oxidation, that a reducing agent is itself oxidized, and an oxidizing agent is itself reduced. Okay, so acid pairs with a conjugate base pairs with a conjugate acid. An acid donates a proton. A conjugate base forms when the acid loses a proton. A base accepts a proton. A conjugate acid forms when a base accepts the proton. The next set of slides are looking at how water is amphoteric. We have mentioned that already. Now, the fact that it's amphoteric means it can both donate and accept protons. Which one it does depends on whether it's classed as an acid or a base. On this slide, we've got some examples. We're using water as both an acid and a base, but it's going to let you see what I mean by a conjugate base and a conjugate acid. So in the first example, we've got hydrochloric acid as our acid. It is going to donate the proton, which gives us a conjugate base of the chloride ion. Water in this case is in our base. We know that the lone pair on one of the lone pairs on the oxygen atom of water can accept a proton and form a dative covalent bond using those electrons, and that we get the hydronium ion. So what we're saying is if water is a base, it can accept a proton and form the hydronium ion, and the hydronium ion is classed as our conjugate acid. If we look at ethanoic acid, our ethanoic acid is going to donate the proton, and it is going to form the conjugate base that is the ethanoate ion. In that case, water is again reacting as a base. It's going to accept the hydrogen ion, it's going to accept the proton, and the conjugate acid formed is the hydronium ion. The next two examples look at water as an acid. So for the first one, our water is going to have to donate the proton. So by donating the proton, the water is going to form the conjugate base, which is the hydroxide ion. Our base in this case was ammonia. We know that ammonia, the lone pair of electrons on nitrogen, can form a dative covalent bond with a hydrogen ion to form ammonium. That is what happens here. So ammonia is the base, and our conjugate ion is going to be the ammonium ion, and that is a conjugate acid pairing up with the base. The final example is a reverse of the one that we did earlier for ethanoic acid. So in this case, our water is the acid and our ethanoate ion is the base. Our water is going to lose or donate the hydrogen proton, and it's giving us the conjugate base of the hydroxide ion. And our ethanoate ion is going to accept the proton and is therefore a base, and it's going to form a conjugate acid. You happy with that? What we're looking at next is weak and strong acids. Now, the term weak and strong, when we come to acids and bases, we've got to be very, very careful with. There is a difference between strong and weak acids and dilute and concentrated acids. Strong and concentrated and weak and dilute do not mean the same thing when we're talking about acids and bases. Okay? Right. What a strong acid is a substance that fully dissociates into ions. It includes things like hydrochloric acid, nitric acid, and sulfuric acid, which you've used. Okay? I can have a strong concentrated acid, and I can have a strong dilute acid. If we use hydrochloric acid as my example, if it was 5 moles per litre for its concentration, that would be a strong concentrated acid. If I picked up the bottle and the label said it was 0.1 moles per litre, that would mean I have a strong dilute acid. Okay? When it comes to my weak acids are acids that don't fully dissociate into ions. So it's things like ethanoic acid, which is vinegar, and you've probably used in school, carbonic acid, which is basically what's used in fizzy juice, and sulfurous acid. You may have seen that you get H2SO3 rather than H2SO4. H2SO3 is a formula for sulfurous acid. It's a weak acid. It only partially dissociates. For our weak acids, we can get concentrated and dilute weak acids. So if I had ethanoic acid at 5 moles per litre written on the bottle, I know that it's a weak acid that's got a high concentration. But I could also get a dilute weak acid. So if my ethanoic acid had 0.01 moles per litre written on the bottle, that would be a weak acid and it would be dilute in solution. Okay? We need to be careful. So if I look at it in slightly different terms, if I get my bottle of Ribena and a beaker and I put 10 cubic centimetres of Ribena in the bottom of the beaker and add 90 cubic centimetres of water, that would be a dilute solution. It wouldn't be a weak solution, it'd be dilute because I've got very little solute and a lot of solvent. If I then took another beaker, I took my Ribena again, and I put 90 cubic centimetres of Ribena into the beaker and added 10 cubic centimetres of water, that would be a concentrated solution. It wouldn't be a strong solution, it would be concentrated because I've got a lot of solute and very little solvent there. Okay, please be very careful with these two terms. Right, next thing we're going to look at is the equilibrium equation and what this means. So if I've got the strong acid, as you can see, I've got hydrochloric acid, it's going to split completely into hydrogen ions and chloride ions. Whereas for my weak acid, my ethanoic acid, we're going to have an equilibrium. We're going to have some molecules that are still ethanoic acid, and we're going to have some hydrogen ions and some ethanoate ions. Okay? This equilibrium is going to be ongoing. So we're going to have some of our ions reacting to form ethanoic acid molecules again. But at the exact same time as a molecule forms, a molecule will dissociate into the two ions. Okay, that's so as we can keep the position of equilibrium the same. Right, we're going to be looking firstly at differences in the chemical properties of equimolar concentrations, weak and strong acids. They have to be the same concentration. So if I start using 1 mole per litre of my strong acid, so if I use 1 mole per litre for hydrochloric acid, I must use the same concentration of ethanoic acid, or I'd be changing two variables. I'd be changing the concentration and whether it's a strong or a weak acid, and my results would be void, they would not be valid. So pHs. pH is actually looking at the concentration of hydrogen ions present. So if I have got my strong acid, I'm going to have every hydrochloric acid particle split into ions. So there's going to be lots of hydrogen ions present. Therefore, I'm going to have a pH of a strong acid, which is around about 0, 1, or 2 on the pH scale. If I've got my weak acid, I'm going to have molecules present. I'm not going to have anywhere near as many ions present. This means they'll be harder to detect, and overall, there will be less hydrogen ions. Therefore, my pH is far closer to 7. My pH of a weak acid is 6 or 5 usually. Conductivity. We're going to look at that in a similar manner. If I've got my strong acid, I've got all my ions present. And we have to remember that conductivity is due to the ions carrying the current. Okay, so if every single hydrogen chloride particle has been split into ions, there's going to be lots and lots of hydrogen ions present to carry the current. Therefore, the conductivity will be high. If I've got my ethanoic acid, I've only got a few hydrogen ions present, but I've also got a lot of molecules. So not only are there going to be fewer ions, it's going to be harder to find them. Therefore, the conductivity is much lower. When we come to reaction rates, if we look at it in the same way, it's going to be the hydrogen ions reacting. If we look at neutralization, that's what it is. So every hydrogen chloride particle has been split into ions. So as soon as I add my sodium hydroxide, every hydrogen ion will react with hydroxide ion, and we're going to have a really fast reaction. When I've got my weak acid, it's going to be harder for it to find the hydrogen ions. Therefore, it's going to not react as fast. Okay, if I'd used a different base, if I'd used something like calcium carbonate, we'd be getting carbon dioxide gas produced as well as water, and we'd be able to see the bubbles of gas. For the hydrochloric acid, these bubbles of gas will form far faster and the reaction will finish faster. Okay, but my ethanoic acid, the bubbles will keep appearing for a long time as more and more carbon dioxide gas is being produced from the reaction, and it will therefore take longer for the reaction to finish. It's just pointing out below this that the reason the rate differs is because of the hydrogen ion concentration, as I've said, and also with the weak acid, the fact that there's an equilibrium between the molecules and the ions. We're now going to look at the similarities between the strong and the weak acids. We are looking at the neutralization reaction again. Now, when our weak acid reacts with the alkali, the hydrogen ions from the weak acid are going to react with the hydroxide ions from the base to form water molecules. With both of the strong acid and the weak acid, this does happen. Okay, so for my strong acid, I'd have my hydrochloric acid here. It would be split completely into ions. This sign here, this sign here doesn't exist. Okay, so it splits completely into ions. So all that would be happening with that one is my hydrogen ions would be reacting with the hydroxide ions to form water. I've got no molecules there except the water molecules that form. And what I'd be left with is sodium ions from the sodium hydroxide and the chloride ions from the hydrochloric acid. They'd all be in a 1-to-1 ratio. However, my weak acid, when I add in my sodium hydroxide, what's going to happen is that hydrogen ions that are present are going to react with the hydroxide ions from sodium hydroxide. This will mean these hydrogen ions, the concentration of them will decrease. Okay, this is going to muck up my equilibrium. If we think back to higher, when we talked about equilibrium, we said that if we decreased something, we would have to shift the position of the equilibrium to counteract the change. So, as these hydrogen ions are produced, we're going to need more ethanoic acid molecules to split up to replenish the hydrogen ions. For this to happen, the equilibrium needs to shift to the right. And this will encourage the breakdown of the ethanoic acid molecules into ions. But every time the hydrogen ion appears, one of these hydroxide ions is going to nick it. It's going to react with it, and it's going to form a water molecule. We will eventually get to the stage that all the ethanoic acid is split down into ions. Okay? This will mean that there will no longer be any ethanoic acid molecules left. It means that substance will be neutralized. What we will then have is our salt formed, we'll have our sodium ethanoate, and we'll have our water molecules. Okay? At that point, where there is no ethanoic acid left, the reaction will have finished. There has been a full neutralization reaction. There are no molecules left. Okay? The volume of sodium hydroxide that's required to do that is identical to the volume of sodium hydroxide that would be needed to neutralize the exact same volume of hydrochloric acid when this hydrochloric acid is of the same concentration. Okay? Now, if I look back here, it's just reminding us that the hydrogen ion is being consumed, so the concentration is being decreased. Because of this, the equilibrium has to shift. It's going to shift to the right, and this means more molecules will dissociate. This is going to keep happening. Eventually, we will get to the stage that all the hydrogen ions that would have been present have reacted with hydroxide ions to produce water molecules, and we will have neutralized the substance. As it says there, at this point, the same volume of base will be needed to neutralize both the strong and the weak acid. The strong and weak acid will themselves need to have been of the same concentration, will have the same volume. It's saying that stoichiometric reaction is the same for the weak acid and the strong acid that are the same concentration, and we need to also have the same base. This can be proved by using the balanced equation. Okay, so if you've got 10 cubic centimeters of your strong acid, which has got a concentration of 1 mole per litre, and you add a 1 mole per litre base to it, you would find you'd need to add 10 cubic centimetres of it. Remember, when you're adding your base, you should be waiting till it's actually finished reacting before you add more base during the neutralization reaction. Okay, this is extremely true for the weak acid because of the equilibrium. When you then take your ethanoic acid and you add 10 cubic centimetres of that acid to a conical flask, and it's 1 mole per litre, and start titrating the base into it, you will find that it's exactly the same volume that's added. All that will happen is it will take longer because the weak acid will take longer to react with each molecule of alkali that's added. Okay? Stoichiometry is just to do with the mole ratio, which is why you can prove it using a calculation. Next, we're going to be looking at strong and weak bases. They follow the same principle. Now, we need to look at base in a slightly different definition here because we're looking at it for neutralization. Okay, we must know that Bronsted-Lowry says that the base, I've purposely gone back, so Bronsted-Lowry is the base, is the substance that is capable of accepting the proton. Okay, but when we look at our acid-base reaction, or neutralization reaction, we need to consider that the base is a substance that will neutralize a hydrogen ion of an acid to form water. Okay, it is accepting it by neutralizing it. So strong bases, like strong acids, they fully dissociate into ions. The ones you'll have heard of and regularly used are sodium hydroxide, potassium hydroxide. In a similar manner to our weak acids, our weak bases partially dissociate into ions. You'll be familiar with ammonium hydroxide, but you also need to know that amines are weak bases. Right, the equilibrium equations for these are, well, we've got our sodium hydroxide showing that it splits up completely into sodium ions and hydroxide ions. There's no equilibrium sign there. But our weak base, we've got here, and we've needed to include the water molecules. Both water and ammonia prefer existing as molecules, okay? But we need them together because the ammonia is going to accept one of the hydrogen ions from the water molecule, okay? The water molecule is donating, therefore is being classed as an acid in this case, and the ammonia is accepting, therefore being classed as the base, okay? Oh, if I'm going to look at conjugate acid and conjugate base, I've said my water is donating, therefore is the acid. That means that the conjugate base is the hydroxide. My ammonia is accepting, therefore is the base. So my conjugate acid is my ammonium ion. If you're not happy with that, don't remember it, go back to the start of the slides and have a look at it again, okay? So first thing we're going to do is look at the differences between our strong and our weak bases in equimolar concentrations. Equimolar being the same concentration, okay? pH, yes, I've said it's hydrogen. We will have some hydrogen ions existing in our alkalis. The number of them will depend on whether it's a strong alkali or a weak alkali or a weak base, okay? There are more in the weak base, more hydrogen ions in the weak base. Right, it might have been easier to say pOH, the differences in the pOH. In terms of the pH scale, it's easier to talk about the hydrogens. So, pH, we're going to have more hydrogen ions in a weak base. This is to do with hydroxide ion, okay? So, if we've got our weak base, we're going to have fewer hydroxide ions. If we've got fewer hydroxide ions, we have more hydrogen ions. That's going to be one way to look at it. Therefore, pH is going to be closer to 7, and it's going to be about 8 or 9 for our weak base. In our strong base, we're going to have very, very few hydrogen ions. We're going to have lots of hydroxide ions though, and our pH is going to be closer to 14. Okay, so the pH is determined by the concentration of the hydroxide ions. The higher your hydroxide ions, the lower your hydrogen ion concentration. The higher the hydroxide ion and the lower the hydrogen ion concentration, the stronger the alkali, or the stronger the base, and the higher the pH number. The weaker the base, the fewer hydroxide ions, the greater the hydrogen ion concentration, and the lower the pH number. Okay, so our weak base has a pH that is closer to 7. It's going to be about 8 or 9. Conductivity, same way as we looked at it for our weak and strong acids. We'll look at the number of ions present. Okay, so if we've got our strong alkali, if we've got sodium hydroxide, we're going to only have ions present, therefore it's going to be far more conductive. If we've got our weak base, if we're going to have ammonium hydroxide, we know that there's going to be a lot of water and a lot of ammonia ions present, and very few ions, therefore there's fewer ions to carry the current, and the conductivity is much lower. Reaction rates, again, it's to do with the concentration of the ions. More ions are present at a time, the faster the rate of reaction. Again, when it comes to neutralization, all ions will eventually react, and we will eventually find that if we were adding an acid by titration to an alkali, that the volumes are the same, but the length of time it's going to take will be longer. As I say, please make sure that when you're doing a titration with a weak acid or weak base, you let the reaction finish before you add in more of your alkali or your acid. Again, there are similarities between them. As I've said, it's talking about a neutralization reaction, and it's talking about what is happening during the neutralization reaction. Okay, so if I look at my neutralization reaction for my ammonia, and I'm adding hydrochloric acid to it, what's going to happen is the hydrogen ions from my hydrochloric acid are going to react with hydroxide ion. That's going to decrease the concentration of the hydroxide ion. You might notice a slight difference in the slide. Instead of changing the whole lot, I've just changed and starting again, I've just changed the error. Right, so we have our hydroxide ion reacting with these hydrogen ions. It's going to decrease the concentration of the hydroxide ions. Therefore, we need to find a way to counteract the shift in the equilibrium, to get the equilibrium back where it should be. The equilibrium is going to move to the right. What's going to happen is these are going to react more. We're going to produce more ammonium and more hydroxide to replace the hydroxide ions that were removed. Okay? This, therefore, is happening alongside. So the hydroxide ions are reacting with the hydrogen ions from here to form additional water molecules. Yes, this is going to affect this equilibrium. These water molecules forming here are not these ones. These are the ones that come from the neutralization reaction. Okay? So as we go through it, we've shifted the equilibrium, as was said there, and what we will eventually find is the same volume of acid is added to both the weak base and the strong base. Sorry, I noticed another typo. So you may have noticed the slight word changing. The bottom paragraph, it says, this means eventually the same volume of base is required to neutral. Shouldn't say that. Sorry, this means eventually the same volume of acid is required to neutralize a strong or weak base of the same concentration and volume. Right, we have been looking at dissociation constants for water, and we know that Kw equals whatever's on the right-hand side of the equation over whatever's on the left-hand side. Now we're going to look at the dissociation constant of an acid. Now, again, it's not just K because it's the dissociation constant we're looking at, okay? So we're using the general, and we need to know about the general equation. If we're using the general equation where HA is our acid, our base is water, we're going to get the conjugate acid, which is our base having gained the proton, and we're going to get our conjugate base, which is the acid having donated the proton. Okay. If we look at this, if we remember back a few lessons ago in equilibrium, we said that if we had a water molecule, because it was a liquid, we used its value as 1. Hence, in the dissociation constant equation, we don't need to put water. So on the top of the equation, we're going to have the right-hand side of our equation. So we need the concentration of the conjugate acid times the concentration of the conjugate base divided by the concentration of the acid. Now, how do we know if it's a weak or a strong acid? That we can tell from the Ka, the dissociation constant value. If the value is large, the equilibrium is going to lie to the right, and effectively this means that the dissociation has been complete. Okay, the acid has fully broken down into ions. But if the Ka value is low, that means the equilibrium lies to the left. It means the substance prefers existing as molecules, which means we've had very little dissociation of the acid or of the molecule, and therefore it's a weak acid. We generally find the acids will fall into one of these two categories. You're not going to be asked about any acid or base that does not fall into the category of being a strong acid or base or a weak acid or base. Okay. The other thing is we're only looking at the value for Ka. We do not need to know about the value for Kb. When we're measuring our weak acids, as we've said, what Ka tells us is how easily the acid breaks down into its ions. Okay, we've already said in the slide before, just to clarify, that small value of Ka tells us that it's a weak acid. Now, we can calculate Ka ourselves. Sorry, I shouldn't have said we can calculate Ka ourselves, which we will do, but at the moment that's not what we're looking at. What we're looking at is that we can use the dissociation constant to calculate something called the pKa. Okay, pKa is just the negative log of Ka, of the dissociation constant of the acid. We can use this information to work out the approximate pH of a weak acid. Okay, so at the moment we've said pKa is the negative log of Ka, and we're saying we can take this a step further and we can use our Ka and our pKa to work out the approximate pH. So how we would do that is we would take our Ka, we'd work out what pKa is, and we'd half it. We also need to look at the concentration of the hydrogen ions present. When we're using this equation here, we will be given 2 of the 3 bits of information, or we can find the missing bit of information on page 13 of the data booklet. Okay? Please be careful though when you're doing the calculation. Sometimes it'll give you a value for Ka or pKa rather than ask you to use the value out of the data book. If it gives you a value, use it. They can give you slightly different values. And if they're giving you a slightly different value for Ka, they want you to work out pKa. The other thing is, I would also strongly recommend, if it says to you to use the Ka value from the data book, you look up page 13 and you don't go, oh, I'll just use the pKa value that's next to it. Use the Ka value. They obviously want to see that calculation. Okay? So there are some key equations that we're going to be looking at. Some of these we have already met, and 2 of them or 3 of them are new to today. So we are familiar with the ionic product of water. We are familiar with the fact that the hydronium ion times the hydroxide ion is equal to 1 times 10 to the minus 14. Okay. We are familiar with pH equaling the negative log of the hydrogen ion concentration. We're going to take this a bit further. Okay. We are going to be looking at the fact that the dissociation constant of an acid can be calculated by looking at the concentration of the hydronium ion times the concentration of the conjugate base. We're going to be looking at the fact that hydronium ion is the conjugate base, and that times the concentration of the conjugate acid divided by the concentration of the acid will give us the dissociation constant. The calculations we're really going to be doing, look at the next 2 equations. Okay? Please remember for this one, that C there is basically the hydrogen ion concentration, okay? So that bit there is this bit here. It's for a weak acid, that's why we need to include the pKa. So, to get our pKa from the Ka, if we're given the Ka or asked to use the Ka value from the data book, we need to do the negative log of Ka. Okay? Right, next bit we're going to be looking at is the actual calculations you're to work through. I've done some examples. I'm going to quickly talk through them, but I would ask you to look at the slides again when you come to do the calculations yourself. So the first one is the questions on page 18, and we'll be looking at question 1 initially. The first set of calculations you want to use pH equals a half pKa minus a half log C. You're going to need to work out both what half log C is and what half pKa is for these. Okay, so question 1, first thing you want to do is to get the Ka value from the data book and work out what the pKa is. Remember, that figure is going to go in there, we still need to half it. The next bit, we're going to work out what a half log C is. In the equation, it told us the hydrogen ion concentration was 0.2 moles. So put that in for your C, take the log of it, and then work out what a half is. So this bit here is running half log C, okay? So when we put them together, we need to remember we're using this figure here, and this figure here is negative, okay? But we would be taking it away. Okay, so for calculating pH, there, we've still got negative, we've still got to do our half pKa, and this is our log C. So 0.5 times 4.770, then we're going to add 0.349 to it. Okay, so that's the answer to the first calculation. Have a go yourself and work through it with this and see how you get on. The second one, you're actually going to have to calculate Ka. You're given the concentration of butanoic acid and you have the pH. So you'll need to do the calculation and rearrange it. First thing to do is work out what a half log C is. Then put that plus the pH value you were given in the question into the equation. Then start rearranging it. Now, to get pK on its own, you're going to have to multiply through by 2. Then, so as we can get Ka, we need to take the inverse log of the negative value for here. Okay, we did do this in calculations the other week there, and please remember when you're doing the inverse log, you put the negative value in. Again, have a go at this one and see how you get on. The questions 3 to 7 work in the same manner as the ones that have just been done there. You will either need to calculate the hydrogen ion concentration or you will need to calculate C. Having said that, first one, I actually worked out the pH. Anyway, work through them, see how you get on. If you can't get the answer that agrees, let me know and I'll have a look at it and see what's what. Questions 8 to 13. This time you need to use the pKa value from the data book and C that's in the question. Okay, you're using the same formula, put the information in. Remember to do half pKa and remember to work out what half log C is. More than likely it's going to be a negative number, so you'll be adding this value onto that to give you the pH. Again, ask if you need help. Next set of questions, you're going to be using the pKa value from the data book, but you're going to need to rearrange these to calculate C. In honesty, I think that is what you were doing here. Okay, so those ones you need to rearrange in the exact same way as we rearranged these ones. Okay. Final question, I've done the first one for you. You're to use the pH and see that you're given in the question and you're going to rearrange it and you're going to work out what pKa is. The reason I did this one was I don't want you just looking at the data book and saying, oh, that's what the pKa is. I also noticed though it doesn't tell you what acid it is. It tells you it's a monoprotic acid. That means it's got one hydrogen ion. Okay, so have a go at that one, work your way through it, compare with this, then have a go at the rest of them. Okay, at the end there's just a reminder of these key equations you need. Okay, remember this log C here, the C is equivalent to that hydrogen ion concentration. Again, any questions about anything, please ask. I know this was a long PowerPoint. You might want to listen to it twice. You might want to scribble some notes down while you're doing it. The choice is yours. Thank you.